But what happened before the Big Bang? What happened before creation?
We physicists have waited 100 years since 1916 for this photograph.
Scientists had been anticipating this moment for more than a century just to take a picture of and understand these black holes. And as it stands, it seems they have gotten some bit of success rates. What precisely does a black hole contain? For years, this unsolved subject has kept a lot of scientists and researchers on edge, and in this video, we'll talk about it. With this latest revelation, Michiko Kaku may have saved the world, even if we haven't had any satisfactory answers in years. What does a black hole contain? Among the strangest and most fascinating things in space are black holes. The name comes from the fact that it is merely a large dead star whose gravity is so great that even light cannot escape. Our knowledge of the universe is put to the test by black holes and their mysterious gravitational pull. Scientists are now able to explore new theoretical avenues through the study of these perplexing events, which range from stellar to supermassive sizes. As of present, we still do not know much about what occurs in these holes, but what we do know is that some answers are becoming clearer. It's interesting to note that there are three types of black holes. Supermassive black holes can reach millions or even billions of solar masses, while stellar mass black holes are between 1 and 100 times the mass of the Sun. The intermediate mass ones, which could serve as a link between their stellar and supermassive counterparts, are still quite elusive. Beyond their apparent function as cosmic vacuums, black holes are important testing grounds for fundamental theories, ranging from general relativity to Einstein's quantum physics and string theory. Even with this, there are still unanswered questions, particularly about the internal mechanisms of these massive objects attracted by gravity. In a simpler term, there would be no way out if one were to walk into the clutches of a black hole. Instead, one would descend into the unknown. So if you cannot find a way out of the hole, how do you get the real truth of what is in it? Despite what most people believe, a black hole is not just a space, but rather a complex sphere composed of two distinct elements, the singularity and the event horizon. The singularity is a point of infinite density with minuscule volume that defies scientific explanation. It attracts everything with an unstoppable gravitational pull. Thus, instead of picturing a vacuum when you think of a black hole, visualize a thick, difficult object that violates the norms of the universe. You cannot see black holes with the unaided eye because of their strong gravitational pull. Rather, to determine their influence on the surrounding universe, scientists use advanced equipment such as massive radio telescopes and gravitational wave detectors. Humanity's progress in comprehending these mysterious entities is demonstrated by some discoveries like the first ever photograph of a black hole taken by the Event Horizon Telescope in 2019 and the detection of gravitational waves by LIGO in 2015. NASA scientists focused on the minuscule core of Galaxy M87, a massive cosmic engine located 50 million light-years from Earth, as it is invisible to the naked eye. Later, astronomers found that a violent, whirling maelstrom of extremely hot hydrogen gas, rotating at 1.2 million miles per hour, was the center of the research. This spinning disk of gas needed a large mass concentrated at its center, weighing as much as 2 to 3 billion suns, to prevent it from violently dispersing in all directions. Something with so incredible mass would be so massive that light could not possibly escape. We now have a black hole as a result, but thanks to technological developments like radio telescopes and gravitational wave detectors, scientists can now study their effects on space. And it doesn't end there. As we all know now, it is not easy to plunge into a stellar mass black hole, but there is something much worse called spaghettification. Maybe this name was coined from the process of making industrial spaghetti, but regardless of where it is coined, you do not want to be a victim of this. Even if you manage to avoid becoming spaghetti, it would be pointless to try to escape the clutches of being crushed by black holes. Recent ideas like loop quantum gravity suggest different scenarios for what could exist inside a black hole. Despite popular perception, matter may compress into a Planck star, rather than reaching a singularity, which might lead to the discovery of new physics domains. Singularities may not be the ultimate fate of black holes. After all, black holes might not form at all because of the granularity of space-time, which would make them ephemeral entities. Perhaps while a black hole may not die for billions or perhaps trillions of years, from our point of view, countless opportunities are waiting inside. Without requiring unproven quantum gravity theories, gravastars present a novel viewpoint on the singularity conundrum. Gravastars are teeming with dark energy, more like a palpable force propelling the universe's expansion, in contrast to black holes, which contain singularities. Slightly different from black holes, gravastars embrace dark energy instead of singularity, which makes them an interesting alternative. Like a black hole's event horizon, matter that falls onto a gravastar becomes entangled on its surface. Nonetheless, the status of gravastars is unknown due to recent data from gravitational wave detectors that question their existence. However, their name certainly has a certain charm, similar to that of Planck stars. There's also another theory that provides a less dramatic explanation for singularities. From this angle, the singularity is warped into a loop by whirling black holes. According to Einstein's hypothesis, passing through this loop could reveal a wormhole and reveal a whole new universe. Because spinning black holes are unstable, they present a special kind of problem. The prospect of traveling across universes is also entertained by calculations that point to the existence of wormholes. The black hole's inner horizon is created by the centrifugal force produced by rotation, which functions as a kind of anti-gravity. In the meantime, the center centrifugal force pushes radiation falling inward towards the singularity from the outside region towards the ring singularity, generating a wall of very energetic radiation. Spinning black holes indeed exist, despite their confusing features. Gravitational waves have recently been observed, and these observations have shed light on their inner workings. The observation of gravitational waves, which are disruptions in space-time caused by black hole mergers, in 2015 marked a major advancement in science. Through the analysis of these waves, researchers have found almost 100 recently produced black holes and have expanded their knowledge of cosmic occurrences. This has made it possible to test general relativity more effectively in harsh settings. Recent developments in the study of nonlinear interactions offer hope for model refinement of up to 10%. This could eventually lead to the finding of even more colliding black holes, which would be a significant step toward improving our knowledge of gravity and the amazing things that happen in the remote corners of the universe. Although the epidemic has caused a temporary stop to operations at the LIGO Observatory, new systems will soon be operational, allowing for further in-depth studies and the identification of more black holes. Astronomers have always been enthralled by black holes, and a new study from the University of Michigan has only made them more so. A provocative theory put forth by academics at the University of Michigan may shed light on the properties of black holes. They speculate that, albeit not in the traditional sense, black holes could be holograms. Rather, they are investigating the interaction between the inside and outside of black holes using holograms as a technique. Under the direction of Enrico Rinaldi, the research explores the idea of holographic duality, which postulates the mathematical interchangeability of particle and gravity theories. This idea deals with the disparity in the computation of the properties of black hole interiors and exteriors, which are both three-dimensional objects but are not computed in the same way. Comprehending holographic duality may play a crucial role in understanding the workings of black holes and revealing additional secrets about these mysterious celestial objects. This idea is explored by Enrico Rinaldi's research, which uses holograms to create a virtual bridge between the inside and outside of black holes, and seeks to determine the mathematical correspondence between particle theories and gravity. Michio Kaku's work aims to reconcile quantum physics with gravity, especially in the area of superstring theory. According to this theory, there are more dimensions than the 4 that humans are aware of, which may help to explain phenomena like wormholes and black holes. Superstring theory is challenging yet has the potential to revolutionize our understanding of the universe. However, the solutions to this theory rely on pre-Big Bang conditions. Superstring theory's incredibly complicated mathematics has given rise to new fields of study. Still unresolved, though, is the issue of a quantum black hole. Researchers found a few months ago that string theory could solve the 10-dimensional quantum black hole problem in 2 dimensions. Although scientists think the issue will be resolved eventually, it is still too early to start making plans for time traveling or interstellar travel using black holes. Similar to Newton's laws, Michio Kaku highlights the importance of establishing initial conditions in string theory. One approach is to utilize string theory to describe the history of the universe, starting with the conditions at the Big Bang. Alternatively, and maybe more ambitiously, we could demand that string theory select its initial circumstances. Notwithstanding these obstacles, strides have been made toward reducing the number of possibilities for comprehending the details of the cosmos. And that is it. What are your thoughts? Let us know what you think below in the comments section, and also click on that subscribe button now. And do not hesitate to hit the notification bell.